here's a conservation of energy problem that has sort of two interesting parts. What we have down here is a spring launcher system. So you can take this orange block, push it backwards this way, distance delta S against the spring. So you can get some potential energy stored in the spring, and you can release the block, in which case it'll start flying back this way. And there's an H right here, which is a sort of the level of a hill that the block can sort of negotiate. And so what we'd like to know then is, say, maybe what is the speed of the block when it reaches the top of the hill there. So that's sort of a pretty straightforward problem here. We can say E initial is equal to E final, and the initial energy, of course, that the spring is storing all its potential energy, 1/2 K times delta S squared. There's that potential energy of the spring, all stored up there. And when it goes up the hill, say the orange block reaches the level up here, when it's all the way up there, well, what does the block have? Well, if it's moving with some speed v, has some kinetic energy in there, then it definitely has its kinetic energy, as I just said, 1/2 mv squared, but it's also now distance h above the ground, so it'll have some potential energy too, mg times h. So this is sort of the time between a straight conservation of energy problem, which you might encounter here. You can figure out various things depending on what the problem is asking for, the spring constant, the compression of the spring initially, the mass of the block, the speed of the block up here on the top of the hill, or the h there. So you can sort of put that together and work on anything that your specific problem might call for. I think there's another aspect of the problem which is worth looking at, is that what would happen in particular if something happened down here where there's a sticky spot right here, or a little bit of friction right here. Maybe let's just say that there's some distance, I'll call it delta D here, where there's a little bit of friction. So as the block comes off of the spring, it sort of slides this way as usual, but then it encounters a bit of friction here before it slides up the incline. So there might be several questions you can ask, will it make it up the incline, or how high will it go, or that kind of thing. We'll set up the equation, let you adapt it to whatever your problem might call for, but we'll look at it like this. We'll assume also that the block has enough kinetic energy or enough energy over here to make it over this frictional patch, so it won't stop on the frictional patch. And so what we'll see when everything is sort of done here is the block will make it past this frictional patch to the right here, start going at the incline. And one way or the other, the block will be here, or whatever its case may be. But I'm going to see a hot frictional patch right there. And this is what we're talking about in class with our barbecue surface in there. The surface will be warm after the block travels over it. So let's just set up the conservation of energy and see what we get. Well, I'll start with E initial is equal to E final as usual here. But because I know I'm going to have this hot surface here, I'm going to have some work due to friction that must be done. So there is a modification between the two cases of the problem here. So the initial energy doesn't stay the same here. I still have the 1/2 K times delta S squared. There's that compressed spring. And what that's going to do is go into the final energy of the block. Now that can be a variety of things depending on what your problem is asking for here. Let's just say that in general here it has some kinetic energy and it has some potential energy. And I'll go ahead and call it an mgy in there. I'm not sure if y is going to be as high as h or what, but I'll just sort of call it that. You can adapt it to whatever you want. So this term here is sort of the final mechanical energy of the system. But now I have this term here of the work that friction did on the block to make this surface hot right here. And I know that the work due to friction here is something like the frictional force times the delta D. And this delta D is the same delta D as this one right here. That's the length over the frictional patch. So if I just sort of continue the problem, I think we'll just wrap it up here. I'll write this one more time. K times delta S squared. All that's going to be equal to 1/2 mv squared plus mg times y. And now this frictional force here will be mu times mg times delta D. That's the work due to friction. So I know that friction is mu times the normal force, and the normal force for a block on a flat surface is equal to mg. So I think this equation here is probably about all you need to adapt to whatever your problem might require here. So once again, run over one more time. I have the initial potential energy of the spring. I have the kinetic energy the block has after it leaves the spring, plus some potential it might obtain as it goes up and down the ramp. And there's the work that friction did in heating up this surface here as the block ran over it here. So a couple questions you might ask, like one of the logic questions is, will the block even make it a height h up this high, given that frictional patch is there? The way you might handle that is you might just say that v is equal to 0 over here. And if you do that here, then y here will sort of become the h, let's say, maximum height that will become. So if you want to sort of see where's the block going to stop, then that'll be where the block stops. But of course the block might be here or here or here. Who knows where it is, but wherever it stops, wherever it reaches its v is equal to 0, it'll have some height here, which I'm calling h maximum. It'll have some maximum height that it obtained when it finally lost all of its velocity here. So that's one particular adaptation of this problem here, is that if you just put an H max in for Y and cancel that term away, say where does it stop, then you could figure out what mu or K or delta S or whatever you might need here to sort of analyze the problem in that regard. But that's certainly one potential outcome of this equation right here. And if you were sure that it was going to make it over the incline, or maybe the problem wants to know, well, what would this delta D need to be in order to achieve some speed up here or something like that, you could certainly adapt the equation that way. But this is your core here that should work in a variety of scenarios here. Again, initial spring potential goes into kinetic of the block plus potential of the block plus the barbecue surface that we see.